right now. If you step outside on a clear autumn night and let your eyes adjust to the dark, you can see it. No telescope required. No app, no special equipment, nothing except your own 2 eyes and a sky free from city lights. Just above the great square of Pegasus, tucked in the constellation that shares its name, there it is, a faint, soft blur of light, barely there, like someone breathed on the sky, and the fog refused to lift. That smudge is the Andromeda Galaxy, and it is 2.54 million light years away. Let that settle in for a moment. The light you are looking at right now, with your naked eye, left its source before modern humans even existed on this planet, before we painted on cave walls, before we sharpened the first stone tools, before the entire recorded history of human civilization. The photons now landing on your retina were already racing through space at 186,000 miles per second, making their long, uninterrupted journey across the intergalactic void. And here you are, on this pale blue dot, catching them with your eyes. No other object visible to the naked eye from Earth is even close to being this far away. The next closest things you can see without a telescope, stars like Sirius or Vega or Betelgeuse, are measured in hundreds of light years at most. Andromeda is millions of light years away, and yet it shows up in the night sky as the most distant thing a human being can perceive with their own biology. That fact alone should stop you cold. But here is what makes it even more extraordinary. For most of human history, nobody had any idea what they were looking at. The ancient Persian astronomer Abd al-Rahman al-Sufi was the first to record it formally. Back in 964 AD, in his book of fixed stars, he called it the Little Cloud. A beautiful description, honestly. A tiny, gossamer smear among the stars, something to note and catalog and move on from. He had no framework for understanding what it actually was. Nobody did. For the next 1,000 years, it would remain a mystery, a curious anomaly in the sky, classified eventually by Charles Messier in 1764 as object number 31 in his catalog of things that were emphatically not comets, assigned the label M31 and filed away. For centuries, astronomers looked at that little cloud and assumed it was part of our own galaxy. A nebula, they called it, the Andromeda Nebula, a pocket of glowing gas, perhaps a stellar nursery, just another feature of the vast Milky Way. The idea that it might be something else entirely, that it might be a whole other galaxy, a collection of 1,000,000,000,000 stars in its own right, floating in the void beyond everything we knew. That idea was so radical, so structurally disruptive to every assumption about the universe, that serious scientists openly debated whether it was even worth entertaining. And then, in the span of a few decades in the early 20th century, everything changed. That little cloud turned out to be one of the most consequential discoveries in the history of science, not because of what it was in itself, but because of what it told us about everything else. The universe was not just our galaxy. Our galaxy was not the totality of existence. We were not even in the center of our own neighborhood. We were one tiny island in an ocean that contained billions of other islands, stretched across distances so vast that even our largest units of measurement feel embarrassingly small. Andromeda did that. That smudge in the sky broke our understanding of the cosmos and rebuilt it into something so much larger and stranger and more magnificent that the old version seems almost quaint by comparison. And it is heading straight toward us. At this very moment, Andromeda is closing the distance between itself and the Milky Way at roughly 110 kilometers per second. That sounds fast until you realize how far apart we currently are, which means we have some time, a few billion years, give or take, before things get interesting. But it is moving. It is falling toward us, pulled by the mutual gravity between two of the largest galaxies in our cosmic neighborhood. And what happens when they finally arrive at each other's doorstep will be the most spectacular event in the history of the local group. This is the story of that galaxy. We found it, what it contains, how it works, what will happen when the two greatest spirals in our corner of the universe finally meet, and whether in the deepest possible long game sense, anyone will ever actually travel there. Buckle in, because this journey covers more than 2 million light years, 1,000 years of astronomy, and some of the most extraordinary physics the universe has on offer. We are going to Andromeda. But first, let us sit with that opening image a little longer, because there is something philosophically important about the act of seeing Andromeda with the naked eye that goes beyond the wonder of the distance. When you look at that fuzzy glow, you are not seeing Andromeda as it is. You are seeing it as it was 2.54 million years ago. The light arriving at your eyes departed the galaxy before the last major ice age on Earth, before our species had fully diverged from our ancestors, before the genus Homo had even appeared in the fossil record. The Andromeda you are seeing is ancient news, delivered at the fastest possible speed, and it has still taken more than 2 million years to reach you. The Andromeda that exists right now, in this moment, is unknowable to us by any current technology. It has had 2.54 million years to change in ways we cannot observe. Stars have formed and died in its spiral arms. The giant stellar stream in its halo has shifted. M31 may have briefly flared and quieted. We simply cannot know. We are always, when looking at any object in the night sky, looking into the past, but rarely at a past this deep. This concept that astronomy is inherently a form of time travel is one of the most profound and disorienting truths about our relationship with the universe. The closest stars are a few light years away, meaning we see them as they were a few years ago. Relatively inconsequential. But as you look farther and farther out, the gap between appearance and reality grows. The most distant galaxies visible to the Hubble Space Telescope are seen as they were more than 13 billion years ago, when the universe was only a few 100 million years old. We are not mapping the universe as it is. We are assembling a portrait of it across time, each object photographed at a different epoch, layered together into a picture that has no single now. Andromeda, at 2.54 million light years, occupies a middle ground in this temporal zoo, ancient enough that our species was not yet what it is, close enough that we can still study it in extraordinary detail. There is another dimension to the experience of seeing Andromeda with unaided eyes. The human visual system is not well suited to appreciating large, dim objects spread across a wide area of sky. Andromeda's full extent, its outer disk and halo, spans the equivalent of about 6 full moons. But our eyes see only the bright, concentrated core, which appears as that single fuzzy spot. It takes both good dark skies and conscious effort to glimpse even the nearer portions of the extended disk. This is part of why Andromeda was misunderstood for so long. Even when people were looking at it through telescopes, they were primarily seeing the core, which looks superficially similar to other objects that are genuinely just clouds of gas within our galaxy. The extended nature of it, the fact that it is a whole other galaxy stretching across an enormous arc of sky, was hard to appreciate visually. We needed mathematics to reveal what our eyes alone could not show us. The mathematics, when Hubble finally applied it in the 1920s, was devastating in the best possible way. It destroyed a comfortable, small-scale model of the cosmos and replaced it with something almost unbearably vast. And that vastness, that sense of scale, is something that the history of astronomy has repeatedly forced on reluctant human minds. Every time we have thought we understood the size of the universe, something has come along to reveal that we had dramatically underestimated it. Geocentrism gave way to heliocentrism. A solar-centric model gave way to the recognition that our sun was just one star among billions in the Milky Way. And the Milky Way itself turned out to be just one galaxy among hundreds of billions. Andromeda was the instrument of that last great scaling up. That smudge in the sky is the ambassador of the modern cosmos. Section 2. The great debate: was there anything beyond the Milky Way? The early 20th century was a strange time to be an astronomer. On one hand, the tools available had never been better. Large observatory telescopes were finally powerful enough to resolve individual stars in distant objects. Spectroscopy was beginning to unlock the chemical secrets of starlight, and photography was transforming what had previously been a purely visual practice into something more precise, more repeatable, more scientific. On the other hand, the universe was, to most astronomers of the time, still quite small. Small in the sense that the Milky Way was thought to be essentially everything. A galaxy of stars, certainly immense by any human standard, but bounded, finite, and alone. The idea that there might be other galaxies, other vast collections of billions of stars, each as large or larger than the Milky Way, scattered throughout an unimaginably larger cosmos, was not quite absurd, but it was not mainstream either. The philosopher Immanuel Kant had floated something like the idea back in the 18th century, calling these hypothetical structures island universes, and a handful of astronomers had entertained the notion. But without hard evidence, it remained speculation. And in science, speculation without evidence is just a very educated guess. The evidence, such as it was in 1920, pointed in multiple directions at once, and interpreting it required making assumptions that nobody could yet verify. This was the backdrop for one of the most famous scientific confrontations in history, an event that has since been called the Great Debate, though when it actually happened, on the evening of April 26, 1920, in the Baird Auditorium of the Smithsonian Institution in Washington, it was attended by a relatively modest audience who had come to hear two astronomers argue about the scale of the universe. On one side stood Harlow Shapley. Shapley was young, ambitious, brilliant, and politically motivated. He knew that a strong performance that evening might help him land the directorship of Harvard College Observatory, which he coveted badly. He had done serious, important work mapping the size of the Milky Way using globular clusters and the Cepheid variable stars within them. And his conclusion was that our galaxy was enormous, roughly 300,000 light years in diameter, with our sun positioned far from the center. This was actually closer to the truth than anyone had previously estimated, and it was Shapley's strongest card. His weaker argument was the conclusion he drew from it, that the Milky Way was so vast, so all-encompassing, that the mysterious spiral nebulae catalogued in the sky were simply gas clouds within it. There was no need for other galaxies. The universe was the Milky Way, and the Milky Way was the universe. On the other side was Heber Curtis. Curtis was older, more established, and possessed of the kind of oratorical confidence that comes from years of practice. He had previously taught Greek and Latin, which tends to sharpen a person's ability to construct an argument. Curtis had been studying spiral nebulae specifically, and he was convinced they were not internal features of the Milky Way at all. They were separate galaxies, each one a vast collection of stars, each one separated from our own by distances that would make the Milky Way's diameter look modest. His evidence included the fact that novae, exploding stars, observed within the Andromeda Nebula, appeared dramatically fainter than novae observed within our own galaxy. If they were the same type of event, that brightness difference meant only one thing: Andromeda was much, much farther away than the boundaries of the Milky Way. Curtis called these objects island universes, borrowing Kant's phrase, and he went into the debate convinced. After the event, he wrote to his family. Debate went off fine in Washington, and I have been assured that I came out considerably in front. Shapley was more measured in his recollections, though he did admit that Curtis did a moderately good job. Neither man was entirely right. Neither man was entirely wrong. Shapley had correctly identified the size and structure of the Milky Way in broad strokes. Curtis had correctly identified the nature of the spiral nebulae. Each, as the astronomer Virginia Trimble later put it beautifully, had hold of portions of the correct elephant. But the debate itself ended without resolution. The audience went home. The papers were published, and the question remained open, a genuinely unanswered scientific problem sitting at the very center of cosmology. What changed everything was a single letter, written in early 1924 by a man named Edwin Hubble. Hubble was working at the Mount Wilson Observatory in California, using the 100-inch Hooker telescope, the most powerful telescope in the world at that time, to systematically photograph M31, the Andromeda Nebula. He was looking for something specific: Cepheid variable stars. Cepheids are remarkable objects. They pulsate, they expand and contract on a regular cycle, brightening and dimming in a steady rhythm. And critically, the period of their pulsation is directly related to their intrinsic luminosity. The longer the period, the more luminous the star. This relationship had been discovered by Henrietta Swan Leavitt, a brilliant astronomer at Harvard who had analyzed thousands of variable stars in the Magellanic Clouds and teased out the mathematical pattern hiding in their flickering. Leavitt's discovery gave astronomers what amounted to a cosmic ruler, a way to measure distances across the universe by simply timing how fast a star pulsated. Hubble found Cepheid variables in Andromeda, and when he calculated their distances, the results were staggering. Andromeda was not a few tens of thousands of light years away, somewhere in the outskirts of the Milky Way. It was based on Hubble's initial calculations, roughly 900,000 light years away, far beyond anything in our galaxy. Later recalibrations, including a crucial 1953 correction by Walter Baade, who discovered that there were actually two distinct types of Cepheid variables, pushed the true distance to more than 2.5 million light years, which is where it stands today. Hubble wrote to Shapley with his findings. Shapley read the letter and reportedly turned to a colleague and said, "Here is the letter that destroyed my universe. It is one of the most human moments in the history of science. A brilliant man confronting evidence that overturned the model he had spent years building, and having the intellectual honesty to name what was happening clearly. His universe was destroyed, and a much larger, stranger, more wonderful one had taken its place. Before we move on from this moment in history, it is worth pausing to appreciate just how strange the situation was scientifically. Both Shapley and Curtis had access to largely the same observational data. Both were extraordinarily skilled astronomers. Both made arguments that were internally coherent, that relied on real evidence, and that pointed in opposite directions. This is actually how frontier science often works. When you are pushing at the edge of what is known, the evidence is fragmentary. The measurements are uncertain, and the right answer is not yet distinguishable from a very convincing wrong answer. The great debate was not a case of a smart person versus a foolish one. It was a case of two smart people wrestling with data that was genuinely insufficient to decide the question and making different bets about which observations to trust and which to discount. This is a humbling reminder for our own time. There are questions in modern cosmology about the nature of dark matter, about the precise value of the Hubble constant, about the ultimate fate of the universe that have a similar character. Real scientists disagree about them, not because some are competent and others are not, but because the data genuinely does not yet resolve the question cleanly. The great debate is, in this sense, not just a historical curiosity. It is a model for how hard intellectual problems at the frontier of knowledge actually work. What made Hubble's discovery so decisive was not that it was better reasoning from the same data, but that it was genuinely new data. A Cepheid variable measured with the Hooker telescope and the period luminosity relationship worked out by Henrietta Swan Leavitt is not an interpretation. It is a measurement. A measured period gives a measured luminosity. A measured luminosity combined with a measured apparent brightness gives a measured distance. It is arithmetic. And when the arithmetic said more than 2 million light years, the debate was over not because someone out-argued someone else, but because reality had spoken. Hubble's discovery transformed astronomy overnight. The great debate was over. Curtis had been correct about the fundamental question. The spiral nebulae were separate galaxies. The universe was not just our Milky Way, but a vast cosmos filled with billions of such structures, each one a galaxy in its own right, each one containing billions of stars, each one separated from its neighbors by voids of almost incomprehensible scale. Humanity's view of its place in the cosmos had been fundamentally altered in a way that it has not recovered from and never should. We are small. The universe is enormous, and one of the clearest illustrations of that fact is the fuzzy smudge in the autumn sky that people had been looking at for 1,000 years before they understood what it was. Section 3. What Andromeda actually is a portrait of a giant. Now that we know it is a galaxy, let us look at what kind of galaxy it is. Because Andromeda is not just any galaxy. It is the largest galaxy in our local group, a gravitationally bound collection of more than 80 galaxies that includes the Milky Way, the Triangulum Galaxy, and dozens of dwarf satellites. And it is enormous. Andromeda spans approximately 220,000 light years in diameter. Our Milky Way, by comparison, is estimated to be somewhere between 100,000 and 160,000 light years across. So Andromeda's disk is noticeably larger. If you could see the full extent of Andromeda in the night sky, not just the bright central region that shows up to the naked eye, but the full disk of stars, it would appear to be roughly 6 times the width of the full moon. That is a galaxy filling a significant chunk of sky. The reason we see only the compact glow is that the outer spiral arms are far too faint for human eyes, and most of what we perceive as the Andromeda Galaxy, when we look at it, is actually just the bright stellar bulge at its core. In terms of stars, the census is staggering. Andromeda contains an estimated 1 trillion stars. The Milky Way has somewhere between 200 and 400 billion. So Andromeda is home to more than twice as many stars as our own galaxy, possibly 3 or 4 times as many. Put another way, if every person alive on Earth today represented 1 star in the Milky Way, you would need to stack roughly 4 Earths worth of people to represent Andromeda's population. It is a city compared to our town. Despite being larger in diameter and richer in stars, Andromeda's total mass is actually comparable to, and may even be slightly less than that of the Milky Way. A major study published in 2025 in Astronomy and Astrophysics, led by astronomers from the Paris Observatory, revised Andromeda's total mass significantly downward, using sophisticated dynamical modeling that incorporated everything from Andromeda's central bar to the giant stellar stream that dominates its halo. They concluded that Andromeda's total mass is around 450 billion solar masses. The Milky Way, by some estimates, contains close to 1 trillion solar masses of total mass, including its dark matter halo. So the 2 galaxies are much closer in mass than their size difference might suggest. The Milky Way though smaller in terms of visible disk, has a more concentrated mass distribution and a particularly massive dark matter halo. Andromeda is classified as a barred spiral galaxy, the same broad category as the Milky Way. This means it has a central structure composed of a bright, dense stellar bulge at the core, surrounded by a bar of stars, from which the spiral arms extend outward like a cosmic pinwheel. The arms wind outward through regions of gas, dust, and star formation, glowing with the blue-white light of young, massive stars being born in molecular clouds. The overall structure, when seen from above in astronomical imaging, is unmistakably similar to our own galaxy, something that makes it uniquely valuable as a laboratory for understanding what the Milky Way might look like from the outside. The central bulge of Andromeda is notably larger and more prominent than that of the Milky Way. It is packed with older, redder stars, the elderly population of a galaxy that has been forming stars for roughly 10 billion years. These old stars have exhausted most of the hydrogen that fuels nuclear fusion, and they shine with a cooler, more golden orange light than the hot blue giants in the spiral arms. The bulge tells a story of a galaxy that was once intensely active in its core, possibly triggered by past galactic mergers that funneled enormous quantities of gas inward, sparking furious bursts of star formation that have since quieted. The spiral arms themselves are not the smooth, perfectly symmetrical structures you see in textbook diagrams. Andromeda's arms are somewhat fragmented and uneven, with regions of dense star formation sitting next to areas that are more diffuse and quiet. There is also a curious asymmetry. One side of Andromeda's inner disk appears more developed than the other, creating a lopsided quality that suggests the galaxy has been pushed around gravitationally at some point in its past. Astronomers believe at least one major merger event has reshaped Andromeda's structure within the last few billion years. Not a collision with an equal-sized galaxy, but an encounter with something large enough to leave visible scars. The evidence for this includes unusual stellar streams in the halo and an outer disk whose motions do not quite match what you would expect from a galaxy that has been left to its own devices. Running through Andromeda's disk are conspicuous dark lanes of dust, thick rivers of interstellar material that absorb background starlight and create dramatic shadows across the face of the galaxy. These dust lanes are regions of dense molecular gas, and they are exactly the places where new stars are currently forming. They are the galaxy's future, held in suspension, waiting for the right conditions to ignite. One of the more technically interesting aspects of Andromeda's structure is its ring-like pattern of star formation. Unlike the Milky Way, which has a more continuous spiral arm structure with star formation distributed relatively evenly along the arms, Andromeda shows evidence of a ring of star formation at a radius of roughly 30,000 light years from its center. This ring is particularly prominent in infrared and hydrogen emission observations, where it stands out as a dense arc of warm gas and young stars. Some astronomers believe this ring is the result of a past collision with M32, which may have punched through Andromeda's disk like a stone thrown into a pond, sending a wave of compression rippling outward through the gas disk and triggering a burst of star formation along the wave front. The ring, in this interpretation, is literally the aftermath of an ancient impact, preserved in the ongoing pattern of star birth billions of years after the collision. Andromeda also has what astronomers describe as a warp in its outer disk. The outer edges of the galaxy are not perfectly flat, but bent slightly, like the brim of a hat that has been deformed. This warp is thought to be the result of gravitational interactions with the satellite galaxies orbiting Andromeda, particularly the combined tidal forces of M32 and M110 as they orbit and occasionally make close passes to the main disk. Warps in galactic disks are actually common. The Milky Way's disk is also warped, and they are generally understood as evidence of ongoing gravitational interaction with nearby companions. In Andromeda's case, the warp gives astronomers a way to infer the orbits and masses of the satellites responsible. Beyond the main disk, Andromeda is surrounded by an enormous stellar halo, a vast, roughly spherical cloud of older stars that extends far beyond the visible boundaries of the galaxy. Studies suggest that the stellar halos of Andromeda and the Milky Way may extend outward far enough that they are already beginning to overlap, meaning that in a very real sense, these two galaxies might already be in the earliest stages of interaction. The halo is also home to Andromeda's system of globular clusters, dense, ancient spherical balls of stars that orbit the galaxy like a swarm of fireflies, each one containing hundreds of thousands of stars packed into a volume just a few dozen light years across. Andromeda has more than 500 known globular clusters. The Milky Way has roughly 150 to 200. This is a striking difference, and astronomers suspect it is partly the result of Andromeda's habit of absorbing smaller galaxies over its lifetime. When you swallow a dwarf galaxy, you often inherit its globular clusters too, adding them to your own collection. This cannibalistic history is written in the distribution and chemical composition of those clusters, some of which have compositions more typical of dwarf galaxies than of a large spiral, and some of which are arranged in unexpected patterns that hint at their captured origins. This is Andromeda in broad strokes, a vast, ancient, complex structure scarred by past collisions, rich with stars in every stage of life, and far more interesting and irregular up close than its serene appearance in the night sky might suggest. Section 4. The stars within a zoo of stellar wonders. 1 trillion stars is an almost meaningless number on its own. It only becomes meaningful when you start to look at what kinds of stars are actually in there. Andromeda, as a mature, massive galaxy with a long and eventful history, contains essentially every variety of star the universe knows how to make. The most common stars in Andromeda, as in every large galaxy, are the smallest and faintest, red dwarf stars. These are stellar misers, burning their hydrogen fuel so slowly and carefully that they will outlive every other type of star by trillions of years. They are far too faint to see individually from our position across the intergalactic void, but they make up the bulk of the stellar census. They will still be burning long after the sun has swollen into a red giant, cooked the earth to a crisp, and faded into a cold white dwarf. Red dwarfs are the long game of the stellar world. At the other end of the spectrum are the galaxy's rarest and most spectacular residents. Luminous blue variables, sometimes abbreviated LBVs, are among the most extreme stars in existence. These are massive stars, dozens of times the mass of our sun, in a state of profound instability. They sit near the absolute upper limits of what a star can be while still remaining a star, balanced precariously between the inward pull of their own gravity and the outward blast of radiation pressure from nuclear fusion happening at their cores. Every now and then, that balance tips and an LBV erupts, not in a supernova, not a final explosion, but a violent, dramatic outburst that blows off some of its outer layers and briefly makes it among the most luminous objects in the galaxy. Andromeda contains several known LBVs, including one catalogued as I Andromeda, which has been observed to fluctuate dramatically in brightness over time. These stars are thought to be in a relatively brief transition phase before their inevitable deaths as supernovae, which makes studying them particularly valuable. They are clocks ticking down to something spectacular. Then there are the Wolf-Rayet stars, another extreme category. These are massive stars that have already burned through their outer layers of hydrogen and are now exposing their inner core regions, where heavier elements are being forged at temperatures of tens of millions of degrees. Wolf-Rayet stars emit ferocious stellar winds that blow material off at thousands of kilometers per second, enriching the surrounding interstellar medium with heavier elements and glowing with intense ultraviolet and blue-white radiation. Their presence is a reliable indicator of recent star formation, because they only live for a few million years before collapsing in dramatic supernova explosions. Finding Wolf-Rayet stars in a region of a galaxy is like seeing fresh footprints. They tell you that something has been happening there recently. In the outer reaches of Andromeda's disk and halo, an entirely different type of rare star holds court: carbon stars. These are evolved red giant stars that have, through a convective process in their interior, dredged carbon up from their cores into their outer atmospheres. The presence of all that carbon changes how the star radiates light, giving it a distinctly reddish hue and a chemical signature quite unlike normal giant stars. Carbon stars are fascinating because they are star manufacturing facilities, producing carbon and other elements in their interiors. And then, as they age and begin to lose mass through stellar winds, spraying those elements into the surrounding space, they are, in a real sense, helping to build the next generation of planets. Deep in Andromeda's core region, astronomers have found something even more ancient and telling: extremely metal-poor stars. In astronomical terminology, a metal is any element heavier than hydrogen and helium. Metal-poor stars are stars that formed very early in the galaxy's history, before successive generations of stellar births and deaths had time to build up a substantial reservoir of heavier elements in the interstellar medium. These stars are relics, time capsules from the earliest epochs of Andromeda's existence, carrying in their compositions a record of what the galaxy was like when it was young, when the universe was still relatively simple, when almost everything was hydrogen and helium, and the complex chemistry of carbon-based life was still billions of years in the future. And then there are the objects that form after stars die, objects that are in some ways even more extreme than the stars that created them. Magnetars are neutron stars, the collapsed remnants left behind when a massive star exhausts its fuel and its core implodes in a supernova explosion. But these are neutron stars with magnetic fields of almost incomprehensible strength, trillions of times stronger than Earth's magnetic field, strong enough to distort atomic structure itself, strong enough to cause the crust of the neutron star to crack, producing brief but enormously powerful bursts of high energy radiation. The detection of magnetar signals in Andromeda tells astronomers something important. This galaxy has seen many supernova explosions, which is exactly what you would expect from a galaxy that has formed stars for 10 billion years. White dwarf stars, the cooling embers of stars like our sun that have reached the end of their nuclear fuel, are distributed throughout Andromeda in enormous numbers. Some of these exist in binary systems, where they gradually steal material from a companion star. When enough material has accumulated on the white dwarf surface, it can trigger a thermonuclear reaction, a nova that briefly makes the white dwarf thousands of times brighter before it fades back into obscurity. In rare cases, if the process goes far enough, the entire white dwarf can be destroyed in a type Ia supernova, an explosion so bright it can briefly outshine the entire galaxy. Andromeda saw exactly this in 1885, when a supernova now called SN 1885A blazed into visibility near its core. An event that, with the knowledge of the time, was deeply confusing to astronomers who could not quite explain why a single exploding star in the Andromeda Nebula was putting out so much light. Every one of these stellar types contributes to Andromeda's ongoing evolution. They process gas into stars, stars into heavier elements, and heavier elements into the raw material for future generations. The galaxy is not a static object. It is a vast, ongoing chemical experiment, building complexity one stellar lifetime at a time. Section 5. The supermassive black hole 8T Andromeda's heart. At the very center of Andromeda, buried beneath layers of stars and dust and gas, there is a monster, Andromeda's supermassive black hole, formally designated M31, has a mass of approximately 100 to 140 million times that of our Sun. Wrap your head around that number for a moment. 100 million solar masses compressed into a region of space so small that light cannot escape it. By comparison, the Milky Way's own central black hole, Sagittarius A, is only about 4 million solar masses. Andromeda's black hole is roughly 25 to 35 times more massive than ours. And yet, for something so enormous, it is remarkably quiet. M31 is classified as what astronomers call a low luminosity active galactic nucleus. It is not the ravenous, radiation-spewing beast that you see at the centers of quasars or highly active galaxies. It is barely doing anything by the standards of supermassive black holes. It is not currently consuming large quantities of material, which means it is not producing the powerful jets of energy and the intense X-ray and radio emission that more active galactic nuclei generate. For most of its recent history, it has been extraordinarily subdued, a giant that appears to be sleeping. A 2025 paper using 15 years of Chandra X-ray observatory data found that M31 shows a roughly constant, very low count rate of X-ray emission, punctuated occasionally by flares. One significant flare was detected in 2013, where the black hole briefly brightened. But even at its most excited, M31 is orders of magnitude less active than the most energetic galactic centers observed elsewhere in the universe. What makes M31 scientifically remarkable is partly the double nucleus that surrounds it. The Hubble Space Telescope revealed in the 1990s that Andromeda's core is not a single concentration of stars, as had previously been assumed, but two separate concentrations, labeled P1 and P2. P1 is the brighter of the two, but is actually offset from the true geometric center of the galaxy. P2 is fainter, but sits right at the center, and it contains M31 itself, along with a compact blue star cluster called P3, packed with hot, UV bright stars that are orbiting the black hole at extraordinary velocities. The best current explanation for this strange double nucleus involves an eccentric disk of old stars, a ring of stars on elongated orbits around the black hole, which creates the illusion of two separate brightness peaks depending on viewing geometry. The stars in P3 orbit M31 at speeds that can only be explained by the presence of something enormously massive at the center. The velocities are so large that astronomers can measure the black hole's mass simply by watching these stars move, the same way you can calculate the mass of the sun by timing the orbit of the Earth. This is one of the few cases in the universe where we have unambiguous, direct dynamical evidence for the presence of a supermassive black hole, not just circumstantial hints, but actual stars moving in ways that cannot be explained by anything except an extreme concentration of mass. How did M31s grow to be so much larger than our own galaxy's central black hole? The answer likely involves Andromeda's history of galactic mergers. When galaxies collide and merge, their central black holes, two separate massive objects, eventually spiral toward each other through a process of gravitational interaction and dynamical friction, ultimately merging into a single, larger black hole. Andromeda has absorbed multiple smaller galaxies over its history, and each of those absorbed galaxies likely brought its own central black hole into the mix. Over billions of years, these mergers would have steadily grown the mass of M31. Could M31 become active again? Almost certainly, at some point. A large supply of gas arriving at the center, perhaps from a close encounter with another galaxy, or from gas clouds disrupted by stellar interactions in the dense nuclear region, would be enough to wake it up. The sleeping giant could, under the right circumstances, produce jets of energy visible across millions of light years. For now, though, it waits, and that, in an odd way, might be fortunate for any complex chemistry or life processes that might be occurring in Andromeda's central regions, which are spared the intense radiation that an active galactic nucleus would produce. Section 6. Dark Matter, the Invisible Architecture. Here is a problem that keeps astronomers up at night, and has been doing so for more than 50 years. If you add up all the mass in Andromeda that you can actually see, all the stars, all the gas, all the dust, and you calculate how fast the galaxy should be rotating based on that visible mass, something comes out wrong. Badly wrong. In a galaxy made purely of visible matter, you would expect the stars and gas at the outer edges of the disk to be orbiting much more slowly than those near the center, for exactly the same reason that the outer planets of our solar system orbit the sun more slowly than the inner ones. The The further you get from the bulk of the mass, the weaker the gravitational pull and the slower the orbital speed. But that is not what astronomers observe. The stars and gas at the outer edges of Andromeda's disk are orbiting just as fast, sometimes even faster, than those much closer to the center. The rotation curve, as it is called, stays flat or even rises at large distances from the galactic core, instead of dropping off as simple physics demands. There is only one explanation that works. There is a massive amount of invisible material out there, providing the extra gravitational force needed to keep those outer stars moving at such high speeds. That invisible material is dark matter. The first person to demonstrate this in Andromeda was Vera Rubin, who, along with her colleague Kent Ford, published work in 1970 showing that the rotation curve of Andromeda did not behave as expected. This was one of the earliest and most compelling pieces of evidence that dark matter exists, not as a theoretical construct, but as a real, physical component of galaxies. Andromeda, the galaxy that 1,000 years ago was nothing but a blurry mark in the sky, became one of the central pieces of evidence that transformed our understanding of what the universe is made of. What is dark matter? Honest answer: we still do not know. We know what it does. It provides gravitational mass. It helps to hold galaxies together. It likely served as the structural scaffold around which ordinary matter gathered in the early universe to form the first stars and galaxies. We know it does not emit light, does not absorb light, does not interact electromagnetically in any way we have yet detected. We know it exists in enormous quantities, the visible matter in Andromeda, and in every large galaxy, accounts for only a small fraction of the galaxy's total gravitational mass. The rest is dark matter, concentrated in a vast, roughly spherical halo that extends far beyond the visible disk. The dark matter halo of Andromeda is enormous. Using gravitational lensing and stellar dynamics to probe its extent, astronomers have determined that the halo stretches out to enormous distances from the galactic center. The dark matter halos of Andromeda and the Milky Way may already be overlapping. meaning that even before the visible disks of these two galaxies begin to interact, their dark matter envelopes are already intermingling. In some sense, the merger between our two galaxies may have already begun, not in a visible, dramatic way, but in the slow, invisible dance of dark matter, clouds pressing against each other across the void. The structure of dark matter within Andromeda is not uniform. Studies using gravitational lensing, the way that large masses bend the path of light passing nearby, suggest that Andromeda's dark matter halo has a clumpy, irregular distribution rather than being a smooth, spherical shell. Some regions contain higher concentrations of dark matter than others. This is expected in current cosmological models, which predict that dark matter forms a kind of cosmic web of filaments and nodes, and that galaxies form preferentially at the dense nodes. But the details of the clumpiness, how many clumps, how massive they are, how they are distributed, are still being worked out, and they carry important information about the fundamental particle physics of dark matter. One area of active research concerns what are sometimes called dark galaxies, possible subgalactic structures within Andromeda's dark matter halo that contain very little visible matter. If dark matter truly aggregates into clumps of all sizes, there should be many small halos that never accumulated enough ordinary gas to form stars. They would be essentially invisible, detectable only through their gravitational influence on other objects. Some of Andromeda's satellite galaxies appear to be extremely dark matter dominated, with mass to light ratios far higher than any normal stellar system could produce. These may be the luminous tip of a much larger population of truly dark subhalos, clumps of dark matter that orbit Andromeda but contain almost no stars. Their existence or absence is a crucial test of different dark matter models. When the galaxies eventually merge, the dark matter halos will behave very differently from the ordinary matter. Stars and gas clouds, when they encounter their counterparts from the other galaxy, can collide and compress, triggering shock waves and bursts of star formation. Dark matter, however, does not interact with itself or with ordinary matter in the same way. It passes through dark matter halos of the two galaxies will interpenetrate, their particles flying through each other, barely affected by the encounter. The resulting combined halo will be larger and more complex than either parent halo. But the dark matter itself will not be heated or compressed or shock triggered into anything new. It will simply redistribute itself around the newly merged stellar system, providing the gravitational skeleton of whatever comes next. The deeper mystery is what dark matter actually is at the particle level. Physicists have proposed dozens of candidate particles, weakly interacting massive particles, WIMPs, axions, sterile neutrinos, and more exotic options, including entire hidden sectors of physics that interact only gravitationally. Experiments around the world have been searching for these particles for decades. Enormous underground detectors filled with ultra-pure liquid xenon or germanium crystals sit in deep mines, waiting for the faint signal of a dark matter particle colliding with an atomic nucleus. So far, direct detection remains elusive. What we have instead is overwhelming circumstantial evidence from galaxies like Andromeda. Evidence that something massive and invisible is there, bending the rules of motion for everything around it. Andromeda, in this sense, is not just a galaxy. It is a scientific instrument. Its rotation, the motions of its satellite galaxies, the behavior of gravitationally lensed background light passing through its halo. All of these are measurements, data points in the ongoing investigation into the nature of the dark universe that makes up most of what exists. When we eventually build telescopes powerful enough to map Andromeda's dark matter distribution in finer detail, we may find clues that no terrestrial detector has yet provided. Sometimes the best laboratory is not underground at all, but 2.5 million light years away. Section 7. Chemical fingerprints. What Andromeda is made of. Light carries information. That is not a metaphor. When a photon of light is emitted by an atom, the specific wavelength of that photon is determined by the internal physics of that atom, by the quantum mechanical energy levels specific to that element. Every element has a unique spectral fingerprint, a set of wavelengths it emits or absorbs that no other element replicates. When astronomers collect light from Andromeda and pass it through a spectrograph, they can read those fingerprints and determine with remarkable precision what the galaxy's stars and gas and dust are made of. This technique, spectroscopy, has revealed that Andromeda, like every large galaxy, is chemically stratified. The oldest stars, the ones born in the earliest days of the galaxy's formation billions of years ago, contain very few elements beyond hydrogen and helium. They formed before stellar nucleosynthesis, the process by which stars manufacture heavier elements through nuclear fusion in their cores, had enough time to significantly enrich the interstellar gas from which new stars were born. These ancient, metal-poor stars are found predominantly in Andromeda's outer halo, orbiting far from the center in random, non-rotating paths, relics of the galaxy's earliest epoch. The younger stars in Andromeda's spiral arms tell a different story. They are rich in what astronomers call metals: oxygen, carbon, nitrogen, silicon, iron, calcium, and the full periodic table of elements, heavier than helium. These elements were manufactured by previous generations of stars and scattered into space by supernova explosions and stellar winds. Each successive generation of stars forms from gas that is slightly richer in heavy elements than the last. It is a slow, cumulative process of chemical enrichment, and it means that a galaxy's stellar population carries within it a detailed history of how many generations of stars have lived and died. The Milky Way and Andromeda show different patterns of chemical enrichment, and those differences carry information about their different evolutionary histories. Andromeda appears to have undergone a more intense early period of star formation, a starburst that rapidly enriched the inner galaxy with heavy elements before slowing down. The Milky Way has had a more gradual, sustained rate of star formation that has continued to the present day. This gives the Milky Way's spiral arms a slightly different chemical composition from Andromeda's, with the Milky Way showing more active ongoing star formation and Andromeda's star forming activity having declined from what may have been a more intense earlier phase. One of the most intriguing aspects of Andromeda's chemistry is found in the outer regions of its disk and halo, where spectroscopy reveals pockets of stars with chemical compositions that do not match the rest of the galaxy. Some of these regions contain elements in proportions more typical of small dwarf galaxies than of a massive spiral. This is a direct chemical trace of past mergers. The stellar remains of smaller galaxies that Andromeda absorbed, their unique chemical signatures preserved in the stars they contributed. These chemically anomalous regions are like geological strata, layers of history deposited at different times, and they allow astronomers to reconstruct a timeline of which galaxies Andromeda has consumed, and approximately when those mergers occurred. The interstellar medium, the gas and dust between the stars, is also chemically complex. It contains not just hydrogen and helium, but molecular compounds, carbon monoxide, water ice, silicates, polycyclic aromatic hydrocarbons, and a host of organic molecules that are the building blocks of the chemistry of life. These molecules form in the cold, dense molecular clouds that dot Andromeda's spiral arms, and they will eventually be incorporated into new planetary systems when those clouds collapse and form stars. The carbon in those planets, the oxygen in their water, the nitrogen in whatever atmosphere they might develop. It all began in the nuclear furnaces of dead stars and the cold chemistry of molecular clouds. This chemical picture of Andromeda is not just beautiful in itself. It has practical implications for one of the deepest questions in astronomy. Is Andromeda a place where life could exist? The presence of heavy elements, the active production of organic molecules, the ongoing formation of new planetary systems. All of these are prerequisites. Chemistry, at least, is not the obstacle. Section 8. Seeing the invisible Andromeda through different eyes. One of the most important lessons in modern astronomy is that the universe looks completely different depending on what type of electromagnetic radiation you use to observe it. The human eye is sensitive to a narrow slice of the electromagnetic spectrum, what we call visible light, wavelengths between roughly 380 and 700 nanometers. But the universe produces light across an enormous range of wavelengths, from kilometer-long radio waves to gamma rays with wavelengths smaller than atomic nuclei. And each part of that spectrum reveals something that the others hide. When you look at Andromeda in visible light, in the kind of light your eyes can see, you see the brilliant starlight of its stellar population, the dark silhouettes of dust lanes blocking light from behind them, and the glowing nebulae of ionized gas. It is spectacular, and it tells you a great deal. But it does not tell you everything. Switch to infrared light, longer wavelengths that our eyes cannot detect, but that infrared telescopes, like the Spitzer Space Telescope, can, and Andromeda transforms. The dust lanes that were opaque in visible light become glowing structures in the infrared, because those cold dust grains absorb visible starlight and radiate it as infrared radiation. The cool molecular clouds where new stars are forming light up brilliantly. The dense, dusty regions near the galactic center, previously hidden behind curtains of dust, become accessible. Spitzer's observations of Andromeda revealed the detailed structure of its star-forming regions with a clarity that visible light could never provide. And the James Webb Space Telescope has pushed this even further, resolving individual stellar populations and gas structures with extraordinary precision. Radio astronomy opens yet another window. Neutral hydrogen, the most abundant element in the universe, emits a specific wavelength of radio waves at 21 centimeters. This 21 centimeter line is one of the most useful tools in galactic astronomy, because it allows astronomers to map the distribution of hydrogen gas throughout a galaxy, even in regions where visible light is blocked by dust. Radio maps of Andromeda reveal that the galaxy's hydrogen gas extends significantly farther than its visible disk. The gaseous envelope of the galaxy is larger than what you see in optical images, blending at its outermost edges into the intergalactic medium. Radio observations have also revealed the presence of synchrotron radiation, a faint radio emission produced by charged particles spiraling around magnetic field lines, which allows astronomers to map Andromeda's magnetic field. The galaxy has an organized, large-scale magnetic field that threads through its disk and influences the flow and distribution of gas. X-ray observations from telescopes like NASA's Chandra X-ray Observatory reveal the hot, energetic components of Andromeda. The supernova remnants still glowing from the shock of stellar explosions, the X-ray binary star systems, where neutron stars or black holes are actively consuming material from companion stars, and the faint emission from M31 itself. X-ray astronomy provides a direct window into the most violent ongoing processes in the galaxy, the places where energy is being deposited into the interstellar medium, where stellar evolution is happening in real time at its most extreme. In 2025, a study using 15 years of Chandra observations compiled the most detailed X-ray light curve ever assembled for M31, revealing its characteristic low-level activity, punctuated by occasional flares. A detailed portrait of a dormant giant. The combined picture from all these wavelengths is a galaxy of astonishing complexity. What looks in visible light like a relatively simple structure, a central bulge, spiral arms, dust lanes, turns out on closer inspection to be a layered, multi-dimensional system in which different processes operate simultaneously at different spatial scales and energy levels, each one leaving its mark in a different part of the electromagnetic spectrum. Future observatories will extend this picture even further. The Square Kilometer Array, an enormous network of radio telescopes currently under construction across South Africa and Australia, will be able to map Andromeda's magnetic field and hydrogen distribution with unprecedented detail. The Nancy Grace Roman Space Telescope will provide wide-field optical and near-infrared imaging of enormous swaths of sky at high resolution, potentially revealing faint stellar streams and structures in Andromeda's halo that have never been detected before. Every new generation of telescope opens new windows on an object that has been studied for a century and still refuses to give up all its secrets. Section 9: Satellite Galaxies and the Giant Stellar Stream. Andromeda does not travel alone. Like our own Milky Way, it is accompanied by a retinue of smaller galaxies, dwarf satellites that orbit the giant spiral under the influence of its gravity, ranging from small but relatively well-formed dwarf elliptical galaxies to near invisible clumps of stars held together more by dark matter than by any visible stellar component. The two most prominent satellites are M32 and M110, both visible even through small amateur telescopes when you observe Andromeda. M32 is a compact elliptical galaxy with an unusually dense concentration of stars at its center, and current evidence suggests it was once a larger galaxy that underwent a dramatic transformation through its interactions with Andromeda. It appears to have been stripped of its outer regions, its stellar disk literally ripped away by Andromeda's gravity, leaving behind a dense, shrunken remnant that has since settled into a compact structure. M110, also called NGC 205, is slightly larger and more diffuse, with evidence of recent star formation and a dusty lane suggesting ongoing internal activity despite its small size. Both galaxies are thought to have experienced significant gravitational interaction with their host during past close approaches. Beyond these bright companions, there are dozens of fainter dwarf galaxies orbiting Andromeda. NGC 147 and NGC 185 are among the more easily observed, both showing the characteristics of dwarf elliptical galaxies with mostly old stellar populations and little ongoing star formation. IC10, on the other hand, is an irregular dwarf galaxy that is vigorously forming new stars, an unusual characteristic for a small galaxy in the gravitational shadow of something as massive as Andromeda, suggesting that IC10 has managed to hold on to its gas reserves despite the tidal forces acting on it. one of the most striking discoveries of recent years concerning Andromeda's satellite system is something known as the plane of satellites. When astronomers mapped the three-dimensional distribution of Andromeda's dwarf satellite galaxies, they found something deeply unexpected. Many of the satellites are arranged in a thin, flattened plane, orbiting Andromeda in a coordinated pattern, rather than being randomly distributed in all directions. This is genuinely puzzling. Standard models of galaxy formation, the cold dark matter models that have been enormously successful at explaining the large-scale structure of the universe, predict that satellite galaxies should be distributed more or less randomly around their hosts. A thin plane of satellites is not something these models naturally produce, and its existence is a genuine challenge to our current theoretical framework. Nobody has yet provided a fully satisfactory explanation for the plane of satellites. Some researchers suggest it could be related to the large-scale cosmic filament, the web of dark matter and gas that connects galaxy clusters, in which the local group is embedded. Others propose that the satellites were not captured individually over billions of years, but were instead created together in a single event, perhaps thrown out from Andromeda itself during a past merger. This remains an active area of research, and it is exactly the kind of anomaly that tends to indicate something genuinely new and important waiting to be understood. Then there is the giant stellar stream. This is one of Andromeda's most dramatic features, an enormous ribbon of stars stretching for more than 100,000 light years through its outer halo, a sweeping arc of stellar material that represents the remains of a dwarf galaxy that wandered too close to Andromeda and paid the price. The gravitational tidal forces generated by Andromeda's enormous mass stretched and shredded the smaller galaxy over billions of years, pulling it apart and incorporating its stars into Andromeda's halo. The stream is a monument to the process of galactic cannibalism, the way in which large galaxies grow by absorbing smaller ones. The giant stellar stream was first detected in detail in the early 2000s using wide-field imaging surveys, and it immediately stood out as one of the most striking and coherent substructures in the halo of any galaxy. Its stars are predominantly old and metal-rich, which tells us something important about the galaxy from which they came. The progenitor dwarf galaxy was itself a relatively evolved system, not a pristine, primordial collection of early stars, but something that had been chemically enriched through its own history of stellar evolution before meeting its fate at Andromeda's tidal hand. The stream's stars follow orbits that trace a consistent path through three-dimensional space, confirming that they are the debris of a single event rather than a random aggregation. Scientists have been able to use the stream's properties to infer the approximate orbit of the progenitor galaxy, the approximate epoch of the encounter, and even the mass of Andromeda at the time, providing a snapshot of what the galaxy looked like several billion years ago, before the stream formed. The giant stellar stream is not alone. Deep imaging surveys of Andromeda's halo have revealed multiple such streams and structures. Shells of stars, arcs, and irregular overdensities that are the accumulated remnants of many past mergers. There is what is often called the northeast shelf, a coherent shelf-like overdensity of stars in the halo that appears to be the wrapping up of a different merger event, the tidal debris of another consumed galaxy folding back on itself after multiple orbits. There are further stellar streams at different position angles and distances. Each one is a story, a record of a smaller galaxy that no longer exists as an independent entity, but whose stars now orbit, scattered in the vast outer halo of the system that absorbed it. Taken together, these structures tell the story of a galaxy that has grown in part by consuming its neighbors. The halo of Andromeda is, in some sense, a graveyard for the galaxies it has absorbed, their stars now scattered into ghostly structures that persist for billions of years before finally dissolving into the general stellar background. What is perhaps most remarkable about this cannibalistic history is that it is not unique to to Andromeda. The Milky Way has its own collection of stellar streams and merger remnants. The Sagittarius dwarf galaxy is currently being torn apart by our own galaxy's tidal forces, and its stars are being wrapped into long streams that circle the Milky Way multiple times. Most large galaxies have histories of this kind. Galaxy formation, it turns out, is not a gentle process of gas slowly condensing into an elegant spiral. It is a rough and tumble history of mergers and cannibalism. With the current state of any large galaxy being the cumulative result of dozens or hundreds of past collisions with smaller objects. Andromeda's halo streams and Milky Way's Sagittarius stream are not anomalies. They are signatures of how the universe builds big things. These interactions are ongoing. Some of Andromeda's current satellites are likely being stripped of their stars as we speak, their outer regions slowly feeding material into Andromeda's halo stream by stream, star by star. Section 10. The collision when Andromeda meets the Milky Way. At 110 kilometers per second, Andromeda is falling toward the Milky Way. That is roughly 250,000 miles per hour, faster than any spacecraft humanity has ever launched. And yet, at that speed, covering 2.54 million light years would take, longer than the current age of the universe, if the galaxies were simply moving through static space. But they are not moving through static space. They are bound to each other gravitationally. As the universe expands and carries most distant galaxies away from us, the mutual gravity between Andromeda and the Milky Way is strong enough to overcome that expansion, pulling them toward each other on an inexorable, slow trajectory that will eventually bring them together. How inevitable is this collision? For a long time, the standard answer was very. Simulations run by NASA researchers and published around 2012 predicted that Andromeda and the Milky Way would have their first close pass in roughly 4 billion years and fully merge into a single galaxy nicknamed Milkomeda in approximately 6 to 7 billion years from now. More recent simulations, incorporating updated measurements of the galaxy's velocities and masses, and including the gravitational effects of the Large Magellanic Cloud and the Triangulum Galaxy, have complicated this picture significantly. A 2024 study from researchers in Helsinki, Durham, and Toulouse, using tens of thousands of Monte Carlo simulations, found that the probability of a collision occurring within the next 10 billion years might be closer to a coin flip, roughly 50%, with the Large Magellanic Cloud's gravitational influence being a significant factor in reducing the odds of a direct merger. This uncertainty is real and scientifically important. Measuring the motions of galaxies 2.5 million light years away with enough precision to predict orbital trajectories is extraordinarily difficult. The component of Andromeda's velocity moving directly toward us can be measured with reasonable precision using Doppler shifts in spectroscopy. The sideways component, the transverse velocity, how much Andromeda is moving across our line of sight, is much harder to measure and carries significant uncertainty. That uncertainty translates directly into uncertainty about whether the galaxies will collide head-on, graze each other, or potentially pass more distantly. But even if a full merger is not guaranteed, it seems at least likely that the two galaxies will experience at least a significant gravitational interaction. And what that interaction would look like is worth exploring in detail. The first thing to understand is that galaxy collision does not mean what car crash means. The average distance between stars in a galaxy is enormous, several light years, in the vicinity of our Sun. When two galaxies interact, the stars within them very rarely actually collide with each other. The odds of any two individual stars striking each other during a galactic merger are astronomically small. What happens instead is gravitational. The two galaxies exert tidal forces on each other, distorting their shapes, pulling material out into long streamers and tails, and triggering dramatic changes in the distribution of gas. The most immediately spectacular consequence of a galactic merger is typically a starburst, a period of intense, accelerated star formation triggered by the compression of gas clouds. when the interstellar gas of two galaxies collides and is compressed by the encounter. It rapidly reaches the density and temperature thresholds needed to collapse under its own gravity and form new stars. The starburst during a major merger can produce stars at rates hundreds of times higher than the normal background rate of star formation. The newly formed stars would blaze with intense blue-white light, and the most massive among them would quickly explode as supernovae, enriching the surrounding gas with heavy elements. For any civilization living in either galaxy during this encounter, if any exists, the night sky would transform. Andromeda would grow from its current fuzzy smudge into a brilliant structure spanning most of the sky. New stars would appear everywhere. The familiar shapes of the constellations would dissolve over millions of years as stars were displaced from their current orbits. The long, steady suburban quiet of the galactic disk would give way to something wilder and more dynamic. After multiple close passes over several billion years, during which the galaxies partially merge, separate, and fall back together repeatedly, the process would culminate in a final coalescence. The spiral structure of both galaxies would be destroyed in the process. The result, according to most simulations, would be a giant elliptical galaxy. Elliptical galaxies are the aftermath of major mergers. Rounder, smoother, lacking the organized disk and arm structure of spirals. Their stars moving in complex three-dimensional orbits rather than the relatively orderly circular paths of spiral disk stars. Milkomeda, if it forms, would be a galaxy of a fundamentally different character from either of its parents. One poignant note: by the time the merger is complete, sometime between 6 and 10 billion years from now, the sun itself will have aged into a red giant, its outer layers expanding to engulf the Earth. The solar system will not be a comfortable place to watch the fireworks from. But if humanity, or whatever intelligence has descended from or succeeded us by that point, has spread outward into the galaxy, there is a real possibility of witnessing one of the most extraordinary events in the history of our cosmic neighborhood. From a vantage point among the newly formed stars of Milkomeda. There is something worth considering about what the sky would look like from Earth or from any planet in our solar system's vicinity during the early stages of the encounter, about 2 billion years from now, well before the first close pass. Andromeda would begin to appear noticeably larger in the night sky than it does today. It would still be a galaxy, still a collection of faint light rather than a solid object. But it would have grown from a small fuzzy patch into something that spans a significant portion of sky over hundreds of millions of years. As the distance between the galaxies closes, it would continue to grow, developing visible structure, arms, a bright center visible even without optical aids on a clear night. Then, around 4 billion years from now, things would get dramatic. As Andromeda makes its first close encounter, the sky would begin to blaze, with new stars being born in the compressed gas. The regions of most intense star formation would glow with the light of hot, young massive stars, creating brilliant blue-white clusters visible across the galaxy. Supernovae would be going off with much greater frequency than they do today. The core of Andromeda, sweeping through or near our part of space, would grow to dominate large stretches of the night sky as an enormous, brilliant condensation of light. The familiar, comfortable patterns of the constellations would be slowly, inexorably scrambled as stars were gravitationally displaced from their current positions over millions of years. And M31, the sleeping black hole at Andromeda's heart, it might wake up. As fresh gas is funneled toward it during the merger, it could begin actively consuming material, potentially becoming a low-level active galactic nucleus. The energy output of an awakened M31 might be detectable from planetary surfaces in the merged galaxy as a bright, persistent point of light concentrated at the galactic nucleus. Whether it would become dramatically energetic, an outright quasar, depends on how much gas it could accumulate and how efficiently it could process that fuel. The long-term outcome, Milkomeda, would be a galaxy profoundly different from either parent. The stars of the Milky Way and Andromeda would be thoroughly mixed, Our Sun, with a probability that simulations estimate at somewhere between 12 and 30%, might end up in the outer suburbs of the new elliptical galaxy, far from its current position in the Milky Way's disk. The night sky for anyone living near our solar system at that point would be dim and sparse by current standards. Elliptical galaxies have less active star formation and fewer bright young stars than spirals. So the night sky of Milkomeda would be dominated by the golden and orange light of older, evolved stars, rather than the blue brilliance of young ones. It would feel, in astronomical terms, like the quiet of old age after the turbulent vitality of youth. This is the ultimate destination of our two galaxies. Not destruction. The stars survive, but transformation. The Milky Way and Andromeda as separate, spiraling structures will cease to exist. What will remain is something new, built from the material of both, carrying in the orbits of its stars and the chemistry of its gas the combined history of two galaxies that lived and evolved over billions of years before arriving at this extraordinary conclusion. Section 11. Could life exist in Andromeda? This is the question that hangs beneath all the others, the one that gives the whole exploration a personal, urgent quality. Could anything be alive out there? Could complex chemistry have assembled itself into self-replicating structures in the molecular clouds of Andromeda's spiral arms? Could planets orbiting some of those trillion stars have liquid water, thick atmospheres, warm sunlit surfaces, where something moved and grew, and however improbably became aware? We cannot answer these questions with certainty. We cannot even answer them with high confidence. What we can do is reason from what we know about the conditions for life as we understand it, and apply that reasoning to what we know about Andromeda. The basic requirements, as best as we can determine them, are not exotic. You need a star stable enough to sustain a habitable zone over timescales long enough for complex chemistry to develop, which typically means something in the range of a K-type or G-type star, not too massive, and therefore not too short-lived, not too small and flare-prone. You need a planet in that habitable zone with access to liquid water, which requires the right combination of temperature atmospheric pressure and stellar distance. You need a supply of the heavier elements: carbon, nitrogen, oxygen, phosphorus, sulfur, that are the building blocks of biochemistry. And you need enough time for complexity to build, which means billions of years of relative stability. Andromeda has all of these ingredients. It has 1 trillion stars spanning every spectral type. It has been enriching its stellar populations with heavier elements for 10 billion years, meaning that metal-rich planetary systems, the kind most likely to form rocky, Earth-like planets, are abundant in its disk. It has spiral arm environments similar to those in the Milky Way's own star-forming regions, where the chemistry of life's precursors is known to develop in molecular clouds. In 2009, astronomers reported possible evidence of a planet in Andromeda, a Jupiter-sized world detected through microlensing, the technique that uses a foreground object's gravity to temporarily magnify and brighten background light. The detection was not definitively confirmed, but the technique itself is sound and represents the most promising current approach to finding planets in another galaxy. Gravitational microlensing does not require resolving individual stars. It simply requires detecting the characteristic brightening signature that a planet's gravity produces as it passes in front of a background star. Andromeda's dense stellar field, particularly toward its core, provides plenty of background stars and plenty of opportunities for such events to occur. The challenges in the search for life in Andromeda are fundamentally about distance. At 2.54 million light years away, we cannot directly image exoplanet atmospheres, cannot search for biosignatures like oxygen or methane in the spectral signatures of individual planetary atmospheres, and cannot detect any of the subtle signals that would indicate biological activity on a specific world. Even with the most ambitious telescope technology currently envisioned, resolving individual stars in Andromeda well enough to characterize their planets in detail is decades or more away, if it is achievable at all. What we might detect, if it exists, is something larger. A civilization advanced enough to build Dyson spheres, enormous structures that capture and redirect the energy output of a star, would produce infrared signatures detectable at Andromeda's distance. A star whose visible light output had been dramatically reduced, while its infrared output remained high, would be a candidate for such a structure. Wide field infrared surveys of Andromeda, of the kind that will become possible with next-generation space telescopes, could in principle detect such anomalies if they exist. There have been searches for similar structures in other nearby galaxies. So far, nothing has been unambiguously identified as artificial, but the searches are far from complete. Radio emissions from Andromeda have also been examined by SETI researchers. The search for deliberately transmitted signals that might indicate an intelligence trying to communicate. No such signals have been detected, but the radio sky is vast. The frequencies are many, and the search has barely scratched the surface. The null result so far tells us very little. One of the most interesting considerations about life in Andromeda concerns the galaxy's history of mergers. This is a double-edged issue. On one hand, galactic mergers are disruptive. They can scatter planetary systems, trigger surges of radiation, and introduce orbital instability into regions that might otherwise have been quiet for billions of years. A planet caught near the interaction zone during a major merger would experience elevated radiation, nearby supernova rates, and the gravitational disturbance of having its stellar neighborhood rearranged. These are serious obstacles to the development or survival of complex life. On the other hand, mergers also bring fresh gas into a galaxy, triggering new episodes of star formation and distributing heavy elements into regions that might otherwise have become chemically stagnant. Mergers can reinvigorate a galaxy's chemistry and create new opportunities for planetary formation in regions that were previously barren. Whether galactic mergers are, on balance, good or bad for life is a genuinely open question. The answer probably depends heavily on where in the galaxy you happen to be situated during the event. There is also the question of timing. Andromeda has been around for roughly 10 billion years, life on Earth took approximately 4 billion years to produce complex multicellular organisms, and another 600 million years beyond that to produce animals capable of looking up and wondering about other galaxies. If similar timelines apply in Andromeda, then any civilization that emerged in the galaxy's earliest epoch of stable star formation would, by now, have had billions of years of additional development time beyond where we currently stand. The implications of that are either thrilling or sobering, depending on how you think about it. A civilization with a 5 billion year head start on us would be so far beyond our current level of technology that we probably could not even recognize what they had built, much less communicate with them on equal terms. The universe is old enough, and Andromeda is old enough for truly ancient intelligence to have arisen and flourished and perhaps faded and been replaced multiple times over. What we know is this: the conditions for life are present in Andromeda. The chemistry is there. The stars are there. The time has been there. Whether any of it has assembled into awareness and looks back at our galaxy with the same curiosity with which we look at theirs is a question we cannot yet answer. But it is not a question we can dismiss. Section 12. The dream of getting there, travel, time, and the impossible journey. Every great horizon invites the question: what would it take to actually go there? The distance to Andromeda is 2.54 million light years. A light year is the distance light travels in 1 year, approximately 5.88 trillion miles. Multiply that by 2.54 million, and you get a number so large it is essentially meaningless in human terms. The fastest spacecraft humanity has ever launched, NASA's Parker Solar Probe, reaches speeds of about 430,000 miles per hour during its closest approaches to the Sun. At that speed, the journey to Andromeda would take roughly 17.5 billion years, somewhat longer than the current age of the universe. Clearly, conventional propulsion is not the answer. The most physically coherent ideas for closing this gap involve two fundamental principles. The first is finding ways to approach the speed of light. Einstein's special theory of relativity contains a remarkable provision. as an object's speed approaches the speed of light, time for that object slows down relative to time for a stationary observer. This phenomenon, called time dilation, means that a spacecraft traveling at 99.9% of the speed of light, itself an enormously difficult engineering problem, would experience time passing much more slowly than time on Earth. A journey of 2 million light years, measured in Earth time, might be experienced by the crew as something far shorter, depending on how close to light speed they manage to travel. But even at 99.9% of light speed, getting to Andromeda would still take roughly 100,000 years of ship time, not a human lifetime. The second class of ideas involves shortcuts through space-time itself. Einstein's general theory of relativity allows, mathematically at least, for the existence of structures called Einstein-Rosen bridges, more commonly known as wormholes. A wormhole would be a tunnel through the fabric of space-time, connecting two distant points in a way that bypasses the need to travel the intervening space. The theoretical appeal is obvious. Instead of crossing 2.54 million light years of void, you step into one end of a wormhole and emerge at the other end, near Andromeda. The practical problems are severe. Wormholes, if they exist, would collapse almost instantaneously without some form of exotic matter with negative energy density, a substance that has not been observed to exist. Stabilizing a wormhole large enough for a spacecraft would require energy and exotic matter on a scale that is literally off the charts of current physics. And no wormhole has ever been observed, even in miniature form, by any instrument we have built. A variant on this idea is the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. Alcubierre showed that the mathematics of general relativity permit a solution in which space itself is contracted in front of a spacecraft and expanded behind it, effectively carrying the spacecraft forward faster than light, without the spacecraft itself moving through its local space at superluminal speeds. The craft would be enclosed in a warp bubble. The problems here are similar. It requires exotic matter with negative energy density, which may not exist amount of energy required in Alcubierre's original formulation was on the order of the mass energy of the planet Jupiter. Later theoretical refinements have reduced the energy requirements somewhat, but they remain fantastical by any current engineering standard. Then there is the approach that sidesteps the biological problem entirely. Send no humans at all. Send self-replicating, AI-directed robotic probes capable of sustaining themselves across intergalactic timescales by harvesting materials from objects they encounter along the way. The mathematician John von Neumann proposed the theoretical basis for such machines, often called von Neumann probes, in the 1940s. A sufficiently advanced civilization could, in principle, launch an initial probe that arrives at a destination, replicates itself using local materials, and sends the copies onward. Over timescales of millions or billions of years, such a network could spread across an entire galaxy or beyond. Whether this is physically achievable with any technology we can currently conceive is a different question, but it has the advantage of not requiring faster than light travel, merely patient engineering. The cosmic obstacles to any physical journey to Andromeda are not merely engineering challenges. They are challenges of survival against the universe itself. The intergalactic medium between galaxies is not empty, but it is extraordinarily thin. A sparse scattering of stray atoms and particles, along with magnetic fields and the pervasive bath of cosmic microwave background radiation left over from the Big Bang. A spacecraft traveling at relativistic speeds through this medium would accumulate particle impacts that, at sufficiently high speed, become devastating, the equivalent of extreme radiation bombardment. Active magnetic shielding might be possible in principle, but the energy costs are significant. Navigation in the intergalactic void is another challenge. Within the Milky Way, a spacecraft could use the predictable, steady pulses of pulsars, rapidly rotating neutron stars, as a cosmic GPS system, triangulating its position from the timing of known pulsars. In the intergalactic void, that system would need to be adapted and extended. the universe does provide other navigational landmarks, but the precision required for a 2 million light-year journey is extraordinary. And then there is communication. A spacecraft departing today for Andromeda at 10% of the speed of light, itself a technology far beyond our current capability, would lose real-time communication with Earth within years. After a century of travel, the communication lag alone would be measured in decades. After 1,000 years, the civilization that launched the mission might not exist in any recognizable form. The probe or the crew would be entirely on their own, an island of intelligence in the intergalactic dark, carrying whatever knowledge and values they had been given at departure, with no possibility of updating or assistance. This is the deeper truth of the dream of intergalactic travel. It is not merely a technological challenge. It is a civilizational commitment on a scale that dwarfs anything humanity has ever attempted. It would require not just new propulsion systems and better spacecraft, but new ways of thinking about time, identity, continuity of purpose across millennia, and the relationship between a journey and the civilization that sends it. The people or machines that arrive at Andromeda, if they ever do, will be related to us in the way that we are related to the microbes that first crawled onto land, connected by an unbroken chain of cause and effect, but profoundly transformed by the journey and the time. Whether that makes the dream more beautiful or more daunting probably depends on who you are. For those of us who find the vastness of the universe not terrifying, but exciting, who look at that soft smudge in the autumn sky and feel not insignificance, but wonder, it is both. The dream of Andromeda is the dream of the possible future, the limit case of what intelligence can aspire to become in a universe that has had 13 billion years to become complicated. That little cloud in the sky, the one Abd al-Rahman al-Sufi wrote about in 964 AD, is not just a galaxy. It is a horizon, and horizons exist to be chased, even when they are impossibly far away, even when the journey takes longer than civilizations last, even when the obstacles are almost beyond naming. It is out there, 2.54 million light years away, moving slowly toward us. A trillion stars, a sleeping giant of a black hole, dark matter halos stretching almost to our doorstep, chemical fingerprints of 10 billion years of stellar evolution, and possibly, something looking back. The journey to Andromeda has already begun. We started it the moment we first wondered what that soft blur of light in the autumn sky really was. Thank you for traveling with this channel. If this journey lit something up in you, drop a comment below. What aspect of Andromeda fascinated you most? Whether it is the collision, the black hole, the possibility of life, or just the sheer scale of the thing, I want to hear it. If you want more of this, a like and a subscribe goes a long way. It is what keeps this channel